ago why you could be interested in this from an ADS-CFT point of view, so I'll try to get into that a little bit. And then there's a second part, which is mostly Mathematica, where I actually also will do a little bit of spectral methods and differential equations, which is not related to tensor networks, but something which I find very useful in most of my, my own computations. So that's the Mathematica part, which is a little bit two separate parts in this talk. Good, so we're now familiar with this picture, but I want to talk a bit more about entanglement because this is the last part of the exercise in Mira you'll get today. So this we all did. The correlators, Jeffrey nicely showed if you put two of these dots there, this Mira is structured in such a way that it magically simplifies, and this is also one of the exercises you'll do today because this is a rather simple tensor network. You still have to put in, of course, all these tensors and all the legs and all the numbers, but this is something you can definitely quite easily compute as opposed to this whole diagram. And then entanglement entropy. So this is then somewhat new, but of course we had all the other lectures, so you're supposed to be now more familiar with this. So one thing I wanted to, okay, so you have your spin sites, and they go on forever because we have a translationally scale invariant Mira, but then we want to just look at part of this system of length L. You trace out everything else, and we obtain this reduced density matrix on these L sites. And it turns out that this reduced density matrix is not in a pure state anymore, even though we started with the vacuum, so it was a pure state. But now it's a superposition of other states. Actually, so this is I think I put on my slide. It's an excited state if you restrict yourself to this subsystem. And then the probabilities of each of these states are given by the eigenvalues of this reduced density matrix. And then because you have a superposition of several states, you can associate some entropy to this, and this is what people call this entanglement entropy, and Horatio already introduced it. It's the sum of the probabilities times the logarithm of the probabilities. And in fact, in conformal field theories, this behaves like the central charge over 3 times the logarithm of the number of sites you're doing, so that is this formula. But well, at least I wanted to share a little bit of my confusing, and I thought about this for the first time, like how come we started with the ground state? How suddenly do we get this excited state? But this is easy to understand, so we trace out all these legs. And of course, we're looking now at a different system to some extent. We're looking at some L of these spins with basically you reduce your Hamiltonian also to this part of the system. So basically, you're not comparing you're in the ground state of the full system, but it's different from the ground state of this subsystem of these L sites. And for instance, in the Ising model, you can really see this. The Ising model is what we study all the time, of course, because it's a very simple model. If you look at the energy of the Ising model, there's this analytic formula for the ground state energy. If you have L of these spins, it's this formula. Well, this you look it up in the literature. And this formula, if you expand it for large L, the energy per site goes like -4 over pi minus pi 6 over L squared. I think this -4 over pi you verified yesterday, day before yesterday, in the lectures using this Mira. But there is this correction. So if you have a very short chain, like you have an Ising model of length L, then the ground state energy is actually smaller than per site than the ground state energy of the full system. And the reason is simply that you can actually put your state in this subsystem in lower energy, namely this energy. So this will be the ground state of this subsystem, but at the cost of increasing all the other the energy of all the other sites. So this is not the ground state of this -4 over pi minus pi over 6 L squared. It's not the ground state of the complete system, but it's just the lowest energy state of this system. So and then the question is, of course, how to expand the ground state of the full system into these excited states of this subsystem, and that's basically what this entanglement entropy is supposed to tell you, and that is why we get this entropy. So this is what I wanted to explain a little bit. At least that's one way of thinking about it. That's how I think about it. Good. So then in the exercise, we want you, of course, to compute this. How do you do this in Mira? I think Jeffrey also showed it very briefly, but I wanted to give you a little bit more detail on this, otherwise it will, I guess, be rather tough in the exercise. So in this mirror, I think we've already seen that this green one was this effective reduced density matrix at every layer in the mirror, which kind of represents the rest of the network. So we can represent this network by some effective reduced density matrix, and then which is supposed to have traced out everything else. And then, so in the picture of the entanglement entropy, I basically put the state here. Here I put the state here, and the conjugate state over here, so the Hermitian conjugate. Here I draw it the other way around. So here the state is here, and the Hermitian conjugate is here, because then the picture looks a little bit nicer. And here you see that indeed I took this reduced density matrix, I put the conjugate state, and I traced out everything to the right, and I traced out everything to the left. And this is then the matrix, which is supposed to be this reduced density matrix, which you obtain by taking the state and tracing out everything. This on its own doesn't help you too much, because if we still have L of these sites here, then if you would really compute this whole network, which is not so easy anyway, but if you would do it, then of course you end up with a tensor of 2 to the power L here, the density matrix, times 2 to the power L over there. So that is not, that won't help at all, because that still grows exponentially. But we're lucky here, because there's a simplification in this mirror, because all these things are unitary and isometries. And if you apply a unitary transformation on a matrix or an isometric transformation on a matrix, the eigenvalues remain the same. So, if we just restrict to this part, then this part below here, say, on this below the line, is just a unitary times isometric transformation. So the eigenvalues of the matrix of this matrix should be the same as the eigenvalues of this matrix. And this is, of course, much simpler, because then we don't have to care about this, and we just are left with 1, 2, 3, 4, 5, 6 legs here, and 6 legs over at the other side. Still a little bit big, but this is doable, at least for these kind of systems. No, this is exact, because because it really it's an isometry. So if you look at it in terms of this quantum circuit, you'll find, well, for instance, what Jeffrey showed is, I don't know if I can easily draw it on the blackboard, but so this is true, but if you would have computed the full density matrix on here, then because of basically these isometries, they take this zero state over here, zero state over there, and this stays here. All these zero states would give you a lot of zero eigenvalues if you would have computed the full density matrix over here. So basically, it's of course, the mirror itself is approximate, but once you have that these are unitaries and isometries, then it's an exact statement that the eigenvalues of this matrix is the same as the eigenvalues of this matrix, basically because of all these isometries which take zeros times this non-trivial network. So any other questions about how this works? Good. So okay. So then I wanted. Let's see. Yeah. Okay. Let me first explain this. So I think Jeffrey also briefly alluded to this, but now when we really know how to construct this matrix, what are we going to get? And I want to explain them why you get this entanglement is smaller than log chi times log L, and that this is also somewhat easy to understand, because if we have this, let's put it like there. So we have this diagram, and it looks like there is an isometry over here, and these are traced out. But then there's one open leg. No, this one goes down to another isometry. This one is traced out. Open leg here. There can be a lot of them, in principle, but at some point, yeah, there can actually be a lot of them. So let's see. So one side of this diagram looks like this, and then the question is, how big is this matrix, this reduced density matrix of L sides? So it will be a big matrix, and one of these indices of this big matrix will be the combination of these 6 legs. So that is, and the question is, what is the size of this, basically of this matrix? So probably, well, some of you these, what should be the size of, if you have 6 of these legs, what should be the size of this matrix? So all of these legs have, in principle, bond dimension chi, except for the lower one, which has bond dimension 2, but let's just assume it's also chi, because asymptotically that will be true. They have all chi, and we have log L of these layers, because if you have every time the length, if you add one layer, you have 3 times as many sides, so there's log L of them. So how many possibilities do you have? Well, this combined index is chi times chi times chi times chi is the total number of matrix elements you can have. So it's chi to the power log L. And then then the question is, what is the maximum entanglement entropy you can have if you have a matrix of chi to the power log L by chi to the power log L, because there's also the other index of the Hermitian conjugate. And well, then we look at the formula. So the entanglement entropy is the minus the sum of all these pi's log pi's. And then you have to realize if the matrix size, let's call it M, is chi log L, that the maximum entanglement entropy you can get if all of these eigenvalues on the diagonal are all 1 over M. Because in this way, you have, your state is an even distribution of all these states, and this is how you create most entropy. If everything would be in one state, the entropy would be 0, and if this is, if it's all is maximally mixed, then it's a maximal entropy. So, well, and of course, the sum of this should be 1, because this is the sum of the probabilities, so it should be traceless. So what do you get? Well, if you sum of all these pi's, log pi's, if they're all 1 over M, well, the sum of these pi's will just give you a factor of M, and in the end, the entanglement entropy will just be, well, it's minus log 1 over M, so it's log M, and log M is exactly this formula, because log, well, if you take the log of this chi to the power log L, you get log L goes down, so you have log chi times log L, which is the formula I wrote here on the slides. Is this clear? So that's not accurate with the factor of 2, right? Because indeed we don't have log L of these sides, because there are 2 times log L of these sides, because you have 1 to the right and 1 to the left. And in fact, the lowest one is not chi, but it's 2. So indeed, so I think I put a twiddle here. So this is accurate in the asymptotic regime. And actually, I want to stress a little bit that this estimate is not super careful, because if you look, for instance, back at this Ising model, what I more or less tried to explain, like these probabilities are really the probabilities that your restricted state is not in the ground state, that the ground state of the full system is not in the ground state of the restricted state. What you find in practice in the Ising model is that, well, if you look at this subsystem, what do you expect the state to be in? Well, there are like a large number of states possible, right? 2 to the power n states are possible, but most of them are highly, highly excited. And if you trace out all these other stuff, then you'll find very few, well, the probabilities to be very highly excited will be very small. So what will happen in practice is not this 1 over M story I'm now making, this is the bound, but in practice all of these mostly are almost 0, right? Actually, if you do a Mira, then this 2 to the power n by 2 to the power n matrix, we just assume that all of these are 0. This is basically the approximation what Mira makes, because the ground state is supposed to be close to the non-excited states. So in practice, you'll never find a reduced density matrix which has all of them equal. And if you do find that, then you know that your Mira has a very bad approximation. So this is really a little bit, this bound is very optimistic. That's one of the reasons why I wanted to explain this a little bit more. Is that clear? So there are some analytic constructions, in fact, recently, like with, I think with perfect tensors, or I think you can construct tensor networks which do saturate this bound. But I would argue that if you look at an Ising model or a real physical system, then it's a very bad idea to use this Mira because usually, yeah, really the top eigenvalue is like 70%, and then it's like 10%, and then it goes down very quickly. So physical systems, I don't know, I don't think so. But there are analytic constructions where you could saturate it, that's for sure. Well, also holographic systems can of course be physical, but yeah, then you're looking at a very strange field theory, I suppose. Okay, and I wanted to say this one thing, which is actually very recent research done by Mo Zacht and Peter Shor, is that it was, I think, usually believed, and Jeffrey kind of told this general story, which is generically true. If you have a local Hamiltonian, you expect that the entanglement entropy for one-dimensional systems is either gapped, and then the entanglement entropy, if L grows, goes to a constant, because it's gapped, so there's no more entanglement between faraway sites. Or in these critical systems, which are gapless, then this entanglement entropy almost always grows like log L, and I think it was generally believed that this is always true. But, well, both of them, they tried to prove this, and then they just, well, by trying to prove it, they found a counterexample. So there are also systems where this entanglement entropy actually grows faster than log L. So in their, if you look at their paper, they have a power law violation of this log L scaling for one-dimensional system. They have a perfectly local Hamiltonian, but the entanglement entropy grows like square root of L. So, well, one of the conclusions you can then draw is that at least for very large L, then the Mira will give a bad approximation to this state. And of course, it's a somewhat made-up state, so it's not very clear if it's physical, but it's, yes? I don't think so. This is also a spin chain, and it's also not a quantum field theory, right? In quantum field, in CFTs, it's not a formal field theory. CFTs, it always goes like log L times C over 3. So I don't, yeah, I'm not completely sure how you would physically interpret the system, but they made it up. If you're interested, you can look in the paper. Anything else? So yeah, so the idea is basically that you're now going to construct this tensor network and just diagonalize this matrix, find its eigenvalues, and compute the entropy for a few of these layers, and then actually you can extract the central charge by looking at that. Okay, then this is Swingle thing on the title, of course. Rob, I think, explained it a little bit, or will explain it more carefully even later on, is that in ADS-CFT, if you want to compute the entanglement entropy of this site over L, then you typically take, or I should also explain it, then there is some bulk ADS, so this is the boundary of ADS, this is the bulk. And then you want to, if you want to compute the entropy in ADS, you want to find a surface which minimizes the length. This was explained in the previous lectures. And this minimal surface is, of course, kind of reminiscent of this kind of curve, because here this is also, this curve cuts the minimum number of bonds. And also if you look at shorter systems, you draw a curve like this, and you can still do more or less the same computation, becomes a bit more complicated. But this structure of computation looks very similar. And this is why Swingle proposed that perhaps this Mira is a realization of ADS, basically. Also because ADS, you're typically led to think that this ADS direction is kind of the scale direction, so it's renormalization group direction. And here in Mira, of course, very naturally, you have this coarse graining, so you go to larger and larger scales as you go up in this Mira. So it's a rather natural conjecture to say that Mira is a realization, these tensor networks of ADS. And in some sense, of course, it also has to be true, because if you put, well, in an ideal world, nobody can actually do it, but if you put some field theory, say n is 4 super-Young Mills in 3 + 1 dimensions, you construct a tensor network like this. It's very tough, nobody knows how to do it, but you can think about it. Then this tensor networks, because it is n is 4 super-Young Mills, by construction, has to reproduce some kind of ADS geometry in the large and strong coupling limit. And it's it would be very nice if you can actually look at these tensor networks and really start with your field theory and do some computations in the tensor networks where you really see like this ADS gravity emerging. So it's a very tempting idea that this allows you to study perhaps emergent geometry from a tensor language. And this is, I think, why I put as a subtitle towards holography from the field theory side. Yeah, by studying these tensors, you can see some ADS gravity coming out. And in this case, you don't even expect it to work, I think, because we're mostly studying like an Ising model. And for an Ising model, of course, you more or less expect to find some quantum gravity or something. Well, it's not strong coupling. It's not large n. So you don't really expect to find this emergent geometry. On the other hand, it's also interesting that you could, in principle, do some kind of quantum computations. And at least this idea is suggestive that you will find some geometry on this slice like you do in this Ryu Takanayagi computation. And in my one but last slide, I'll show you a little bit why I think that this is actually very hard to make it work, but it's a very tempting idea. And many people have written papers about it, and Jeffrey, I think, said yesterday that perhaps it's not really that this is ADS, but it's perhaps more like de Sitter because of this causal structure, and this is a very active topic of research. But I want to stress that also part of the idea to put these two lectures from this in Mathematica and Jeffrey together is that if you want to make this more precise, all these papers, they basically draw these nice pictures, and it's very fancy. But it would be nice if somebody also does some actually computations in these tensor networks. If you want to claim things like this, that you're doing quantum gravity, you're doing emergent gravity, then you would want to compute things in tensor networks, and that's why we also thought it was useful to introduce this in Mathematica, which now you try it a little bit in the exercises. So this is basically what I tried to a little bit explain, gravity as an emergent force. This is the, well, to some extent it has to be true by definition, but it would be nice with the tensor networks perhaps to make this precise. Well, I don't have to introduce this ADS-CFT because we had excellent lectures about it. But there is this caveat, of course, if we try to apply this very naively to the Ising model, then we don't really have this large tensor uncoupling limit, so we don't really expect classical gravity to emerge for simple tensor networks like we're studying in the exercise classes, and it's actually not so easy to find more complicated tensor networks. At least I tried that a little bit. Okay, this is Ryuta Kaniagi. I put it on the blackboard. We also saw it in previous lectures. I want to just show you two results, which I think give you perhaps some insight. So this is one result which I wanted you in the exercise to reproduce. I think 3 points of these. So this is entanglement entropy as a function of L. Some of these points are a little bit complicated because they correspond to tensor networks with this dashed line. So it's a little bit of a complicated tensor network. You can still compute it, but it takes a bit of work. But there are these simple lines like this one, where I thought in the exercise you can compute it. So there are 3 of them which are simple. And then you can compute the entanglement entropy as a function of log L, in this case, plotted. And you see that all these points nicely line up on a straight line. The R squared is very small, so it's really straight. So and you get this I plot 3 times the entanglement entropy, so that the coefficient in front of the log L is really the central charge. So you extract from this tensor networks nicely the central charge, like I think Jeffrey also showed, but it's nice to see it in a plot. And yeah, I mean, also note that we don't have any problems with like infinities, regularizations, all that. I mean, this is just a matrix computation. And of course, the whole theory is regularized by this lattice. So in Horatio's lecture, I think we saw a little bit of these complications if you look at actual field theories. And that's, of course, also the nice theory. But here, this is a very natural way to regularize these theories. Is there questions about this? Okay, so this is my last slide on what a little bit of my confusion is perhaps on this ADS-Mera conjecture. Something I wanted, so this works very nicely, of course. So this entanglement entropy and this Ryuta Kaniagi prescription, it all seems to work. But on the other hand, this log L scaling has to be true for general CFTs. So the fact that the entanglement entropy goes like log L, so this bound is not saturated at all, in fact, actually. You just compute the spectrum, you compute the entanglement entropy, and it goes like log L, because basically it has to work because we're looking at this conformal field theory. But what I wanted to do is to get more of a local feeling what this geometry looks like on these kind of lags. And so one thing I tried, and I think you can try many other things, is to assume that perhaps, so basically you have this complicated tensor networks like this with these open lags. What perhaps is true is that this is a very complicated tensor network, but in some regime, perhaps it's true that these 6 lags, which, okay, let me draw it like this. Well, it's not super nice. That these 6 lags can be viewed as just a direct product of some other tensors, which could, in principle, make this ADS-Mera picture more precise. So if this complicated tensor, which you can compute, but it's not very insightful, well, what you basically want to do is, along this geodesic, you want to extract local quantities on each of these lags. Otherwise, you cannot really make sense of this idea that there is some metric emerging on this curve. And what I tried in this last picture is just assume, perhaps, that these 6 legs, or this complicated tensor, is just a product of individual tensors like this, where each of these legs has its own entanglement entropy, and maybe they are all the same, and this entanglement entropy of each of these legs is just the metric on this leg. Well, you never really know. In this case, it doesn't work, and perhaps it works in theories of gravitational dual. And the nice thing is that if this tensor is really a product state of different tensors, I'll leave it as an exercise, but you can very easily show that the total entanglement entropy of this total tensor is just the sum of the entanglement entropy of the individual tensors. For Renyi entropy, it's actually not true, but for entanglement entropy, because of this logarithm, you'll find that if it's a product state, you just add up the individual leg entropies, and it should be equal to the sum of the sum of it should be equal to the total entanglement entropy. And if I then did this, I got some rather not so nice results. So you see what I did. I took this entanglement entropy. I assumed it was a product state. I just added up the entanglement entropy of the individual legs. And what I got is, well, at least it's a little bit of a mess too. It still grows, but you have more legs, so you probably expect that. And you see that this coefficient in front of the log L now is not 0.5, but it's 2.8. So this basically shows you that these legs are not at all in a product state of these individual legs. If this would be true, I think you have like a nice local interpretation of perhaps some kind of geometry or something like that. But this big tensor is not like that. So this is something I tried, and to make this connection ADS-Mira more precise, and more or less it's more of an encouragement for you to try other things and to really see if we can do some precise computation with this. Good, then I think I want to go back a little bit to the Mathematica side. Okay, good, so let's see. So one thing Jason mentioned, which I think is very nice, and which you can also do, is what I always do in my projects in Mathematica is to make these packages. And I think Jason already showed you a little bit how to do this package. You just make some initialization cell, you can do save as a package. But I have this really other nice, well, it's basically, it's not even a trick, it's just an option somewhere. So what I have in my Mathematica is always to have, if you go to Edit, Preferences, Advanced, Option Expected, Notebook Options, File Options, Auto-Generated Package, and you set it to Manual, then you'll find that every time you have an initialization cell and you save the notebook, then it automatically generates the package. So this Mira package is nothing fancy like begin package and all that. I just put in some initialization cells like this ncom. I have this option turned on, and I save it, and it creates this package, and you have all used it. And in some sense, it's super simple to make these packages. And well, of course, you can always wonder, I mean, is it useful to have packages or not? You can also write it in one big notebook. But I now do this for all of my projects, because it turns out that if you do this kind of Mira or any other kind of computations, usually, well, you start first doing the Ising model, but then you want to do another model. And it usually is very easy to just then have this package and just have one option. Well, now we do the XX model. If you look at my package, you can do the Heisenberg model. You can put in all these kind of other models, and you just have separate files for separate models. And you just, you load the package like this. I have this command do a model, and then instead of the Ising model, I put a different model, and it still works. And I have this in all separate notebooks. I don't know, also in ADS, you collide some things or something like that. You have some different parameters. You just have a package. And well, one thing I put in these packages, for instance, I wanted to show you this I guess can I do this like this? What I use a lot is this called ADS shockwave collisions. I have a package like this. It doesn't really matter how it looks like, but I have all kinds of commands, and this is the whole thing which does all the numerical computation. But in the end of the package, I put like a few of the standard values, and it's quite nice to put this all at the end, so that the whole notebook doesn't depend on any of these values, but these are just loaded in the end. You just load this package, and if you then change these values, of course, a few of them, it will just do the same type of computations, but with slightly different values. So I use this a lot because you always want to vary these values a little bit to check for robustness. So this is how I use these packages, and one of the crucial things is, I think, this option to generate these packages automatically. So this was what I wanted to show you. Then there was this, well, the ncon thing, of course, and one thing I wanted to show you which is probably something you shouldn't try at home, but in this Encon, this Encon thing actually supports CUDA, which is nice because you actually can put it on a graphics card instead of a real processor. And it's so easy that I wanted to show it because, well, this matrix multiplication, so some of you might be familiar, a processor has a few number of cores and can do some multiplications very fast, but the graphics card has a lot of processors, which are a little bit more slower, but it has maybe like 1,000 processors. And if you can do this all at the same time, if they work all at the same time, it's much faster than a processor, because you just do 1,000 multiplications at the same time. And matrix multiplications, which basically what these tensor networks computations are matrix multiplications are just like that. If you can do 1,000 at the same time, it's basically 1,000 times faster. So that's why you would think that this CUDA works very nicely. And well, how do I do this? I mean, in this package, it's just normally CUDA is false. But if you then do, instead of, basically this is command, use CUDA, and then it just loads the CUDA package. So if I just use, okay, I first wanted to show you how it works without CUDA. So I do the same thing as we did the day before yesterday. So I have now this operator, this WU operator. I put the bond dimension to 18, otherwise it's much too fast. You don't see any difference. So without CUDA, it takes 0.22 seconds to contract this Chi18 sequence we did yesterday. And now I do this use CUDA. So what does it do? It loads the package. It sets CUDA to be true. And instead of now so there's this, I use in the Mathematica package this dot AB. And if it's CUDA, then it does the CUDA dot. And if it's not CUDA, then it does the normal dot product. So it's as easy as that, with the subtlety that the CUDA dot, so the CUDA dot only multiplies matrices by matrices, whereas the normal dot product can do also tensors times tensors. So I had to kind of do an array reshape, which perhaps makes this CUDA dot a little bit slower. But that's a subtlety, and it's just using CUDA dot or normal dot. And then what it will do is, you'll see, well, we'll try the same computation with CUDA. Does it work? Well, the first time is a little bit slower, perhaps, because it really needs to load this CUDA. And the second time, indeed, it uses, I think now if I look at my graphics card, then indeed it says GPU activity, and it's on Mathematica kernel. So now it just does everything on the graphics card. Unfortunately, this is a laptop, and my processor is very fast, and my graphics card not so much. So as you see, it actually gets a little bit slower. But if you have a desktop with a very fancy graphics card, then the expectation is that it would be faster. But because it's actually not, so that's why I put it as don't try this at home, perhaps. Also, the graphics card runs more easily out of memory, of course, because there's less memory on the graphics card. On the other hand, I do actually use it because now what I can do is I have this package. So if I want to do 2 of these tensor network models, I do 1 on the CPU and 1 on the GPU, and you can do 2 things at the same time. So that's nice. But it's something you don't use very frequently, but it's also very easy, as you see in this. Just
while you're there, just do CUDA Q and please don't. Just CUDA CUDA and Q. I'll just point out that open bracket, close bracket, and with the Q on the end of it, open bracket, close bracket. And so his laptop actually supports CUDA. It's not all laptops do. So just test that first before you actually see that it works. And you go, oh, it's not working. You won't actually see it if your laptop like.
That's true. I mean, and of course there are tutorials about this. You can do the CUDA information, and it will give you indeed like what kind of graphics card you can have more graphics card, and it will. Well, this apparently is this GeForce 860, and sometimes you have to, if you have a very old laptop, it might support CUDA, but it does it in single precision, which is only 8-digit precise. So you have to check a little bit if your graphics card actually supports double precision, otherwise it's quite useless. I looked before buying the laptop that it supported this. That's actually true. But most laptops now do actually. Okay, so that was basically what I wanted to do about Mera, entanglement, and the last part of Mathematica, and I hope we'll work a little bit more in the exercises on this Encon, but if there are more questions about this, otherwise I'll move to different things. Okay, so then it will be different things, and the different things is what I do is actually a little, well, perhaps this last slide is a bit of is almost advertising, but what I actually do a lot is not these tensor networks, but what I do is solving Einstein equations in anti-de Sitter space-time, and this is basically, well, doing these pictures to have a model for heavy ion collisions in ADS or something like that, and I don't want to tell you about the details, but I thought it was useful to advertise a little bit, because there's also this website where if you're interested in these type of calculations, so this is solving Einstein equations in ADS. I actually recently, in June, gave some lectures in Iran about how to implement this in Mathematica. And if you download these files, there are some slides on how do you get Einstein equations, what do you do with them, and how do you put them in Mathematica. And there's a, well, at least as far as I know, the simplest Mathematica notebook possible, which does calculations like this, where, for instance, is this stress energy tensor you get on the boundary field theory for ADS. So here you see, you start, well, I don't want to explain all the details, but you have some energy density, some pressure, some transverse pressure, longitudinal pressure, and you see they start very far from equilibrium, but then dynamically they thermalize. So this is what is called holographic thermalization. In the isotropic case, they go nicely, become all equal to each other, but it can also do some boost invariant geometries. It fluctuates a little bit, but then it thermalizes, and you have basically you relax down to an ADS black hole. So if you're interested in this, you can look at these files and slides to do these kind of differential equations. But what I wanted to explain now in this lecture is what I think is crucial for this type of computations, which is how to solve differential equations with spectral methods. And well, it always sounds a little bit complicated, but it's not, and that's why I wanted to explain you a little bit how to do these spectral methods in Mathematica. First, of course, you can do it with NDSolve, but I don't want, so I also explain how to not do it with NDSolve. So what I want you to look at, and in the Einstein equations, these kind of type of differential equations arise very frequently, are linear differential equations, and I put here just a completely random example. So so let's see. So we can do it. So this linear differential equation is just that well, I just put some random factor, 2 plus x, y prime prime. You see it's linear in y. And here there's some factor, you can put some source, you can put basically any function, and this whole scheme will go through. But I took a relatively simple function because now Mathematica can, in fact, solve this also with DSolve. So we're looking at to solve this differential equation and put some boundary conditions. At y minus 1, it should be 5, and at y1, it's minus 1. As you see, it's actually a little bit of a tricky differential equation, but because you see at x minus 2, there is a divergence, but since the boundary conditions are a little bit far away, we hope it should be fine, and we'll see that it is actually fine. So if you solve it analytically, well, it's maybe even impressive that Mathematica can actually do it. It looks a little bit like this. And if you look at this, the DSolve at this function, you can, I guess you should actually be able to plot it. Oh yeah, put the plot over here. You'd have to take the real part because to evaluate this, you get some small imaginary parts, and the function looks a little bit like this. So this is just the normal DSolve or the normal NDSolve. They'll get more or less the same number of points. But I want to illustrate how to solve this with spectral methods, and then we are going to compare with the analytic solution. So the idea behind spectral methods, maybe I should draw it on the backboard a little bit. So let's see. So the idea behind spectral methods is basically that you expand your function in terms of, so you have x and your function here, and well, in this case it went from minus 1 to 0, but from minus 1 to 1, but let's just do it 0 to 1. It doesn't matter to illustrate the idea that you have some functions which are called these Chebyshev polynomials, and the first one is just a constant. The second one looks like just some oscillation. Or maybe it goes to minus 1, actually. That would make more sense. And then it just keeps on going like this. So there's also one going like this. And then it oscillates more and more. And what the idea is of these Chebyshev polynomials, that we are now going to expand this function, but we were trying to solve it, in terms of these Chebyshev polynomials. And it's much like Fourier series, where you expand everything in sines and cosines, except that we now have a finite grid. So in this case, from minus 1 to 1, or here from 0 to 1, you can just rescale and do your coordinate transformation. That's very simple. And then if you have this function expanded in terms of these Chebyshev polynomials, say we take 20 of them, the statement is that usually you can approximate a function like this very, very accurately. You're perhaps probably more familiar with that if you just have a few of these Fourier mode, that any periodic function can be very easily expanded in terms of these sines and cosines. So that's the idea, and if you have then the expansion in terms of these functions, then to compute the derivative, you can do it analytically. So you just basically have your f approximate, so it's a spectral approximation, it's just the sum of 0 to n of these Chebyshev things, and then everything, if you assume it like this, then you can solve for all these, for derivatives of this analytically. But that is probably the background, but in practice it's much easier than this, because what we actually will do is not use spectral methods directly, but what most people do is they use pseudo-spectral methods. And what you do with pseudo-spectral methods is you just take this function and you evaluate it at a few of these grid points. So the function looks perhaps like this. And then the trick of these grid points is that they're closer to the boundary, and then they go further apart, and then they're closer to the boundary again, and they have a particular form. And the idea is that if you know the function on these grid points, you can change bases into this Chebyshev approximation, compute the derivative analytically in the Chebyshev approximation, and then go back to your grid points and get the derivative on these grid points. And this is very useful because if you just work with this, then you don't have to care about anything. You just want to know what is the function on the grid points, and then basically your f is just a vector, which is the value of the function on all these grid points. And then you can go, in principle, to this basis and compute the derivative and all that. I mean, that in principle, that's how it works. But in practice, of course, differentiation. So if you want now to take the derivative of f, the x derivative of I, then this will also be another vector on these grid points, right? So that will be the derivative. So here it will be approximately 0, then it will be negative, and then it will stay negative. No, it will, and it will go to 0 again, right? So this is how the derivative of f will look like. And what you realize is that differentiation is a linear operator, as you know. So if you have a vector and you have a linear operator, then this differentiation is just a matrix which we call D. Actually, I call it D-spec because it's a spectral method. And this is basically all you need to know about spectral methods. So we have some grid points. We take the function on the grid points. It's a vector. And if you want to differentiate it, you get another vector. Yes? Why I took this Chebyshev things? What? Yeah, so in principle, I guess it's true. I mean, you can expand in any types of basis of functions. So like Fourier basis for periodic ones, Chebyshev basis, if you have some radial symmetry, you can do in radial polynomials. Yeah, for intervals like this, these Chebyshev polynomials, they're just the most convenient. And one of the nice properties, which I'll use in a moment, is that these Chebyshev polynomials are actually just polynomials in X. So if you have so this is probably why they're the easiest, or also why they're all analytic. So if you take the first 30 of these Chebyshev polynomials, they're all linear combinations of 30th order polynomials, x to the power I 0 to 30. So this is a 30th order polynomial. And all of these Chebyshev polynomials, if you write it out in the definition, they're all polynomials in X. So this is, yeah, so this is why they're called Chebyshev polynomials. So that's why they're probably the easiest way to do. But you can try other things, but this is definitely the simplest thing to do, and this is usually very accurate. So how does it look like? So the essential thing here is that you have to take these grid points, and these grid points, they are at the cosine of r pi nx minus 1. So what does this mean? It means basically that, so I have a number of points. I call it nx here, and I take the cosine from 0 to x. So you see that the cosine, of course, it starts at 1 and it goes slowly. First it goes slowly and then it goes faster, and then in the end, at cosine equal to pi, it goes more slowly again. So we get exactly what we wanted over here, is that we get more grid points in the beginning, and then a fewer in the middle, and more grid points in the end, and you really need this to get accuracy near your boundaries. So this is the whole trick you need to kind of know about this spectral method, that you have this table of grid points which look like this cosine. The minus 1 doesn't really matter, that's just switching how you do it. And then the trick is to build these differentiation matrices, and there are several ways how to do this. So let me put this in a grid and take 25 grid points, And then I see that x goes indeed from -1 to 1, where you see that that here the difference is the distance between the points is much smaller than in the middle of the grid. So we have just 25 grid points. Okay, maybe I should have said this before. The advantage of spectral methods is really because you do this exact conversion of basis and back, and you do the exact differentiation, that is a very accurate scheme. So if you just use 25 grid points, which doesn't look like a lot, well, you can get easily like 10, 15-digit accuracy by using only so few points. And this is why this is usually very fast, because it's so accurate. And yeah, basically because you expand all these functions in terms of 30th order polynomials, so the mistake you make will go something like the grid point size to the power 1 over the grid point size to the power, no, the grid point size to the power 31 if you take 30 grid points. So this is, the more points you use, the higher polynomials you're expanding in, and the more accurate your scheme grows, because you're doing this differentiation in these spaces exactly. But, okay, so I was, perhaps it's not completely coherent, but now we have these grid points. We have, in principle, we can construct a function on these grid points, and we're interested in what is the derivative of this function, and we want to construct this matrix. And there's several ways to do it. One way is to do it analytically, like I said, and if you look it up in the books, then people have done this, and you can actually find what is the value of this matrix for n number of grid points in the books, and you just put it into Mathematica. This is how people usually do it. But in fact, there is also a Mathematica command for this, which is what I wanted to show you in this lecture. So this is called the finite difference derivative. So ND of finite difference derivative. So you just have, this is the first derivative, this is the number of grid points, and this is the difference order. So in fact, this finite difference derivative doesn't construct for any type of grid. It interpolates the grid points with a polynomial, and then of a certain order, and then it approximates with this differentiation matrix method I just explained. It approximates the derivatives at these points, and it constructs this called differentiation matrix, which you also get out of this finite difference derivative. But as I just told you, this kind of spectral method just uses all of the grid points and expands it in all of these polynomials. So basically, the spectral method is a special case of this finite difference derivative, where the difference order is just, you use the maximum number of order, which turns out to be the points -1, because if you have this polynomial, if you have a second order polynomial, you need 3 points, so there's a -1 over there. So this is the order, and then Mathematica just constructs this spectral differentiation matrix for you. And now, one other thing I wanted to show you is that you might not know this command, and I didn't know it myself to some extent, but I learned this by looking at the NDSolve tutorial, which I recommend to you if you want to do any kind of numerics or differential equation. I found it a super useful tutorial. So if you go to NDSolve, there are these tutorials, and this one I think is from the advanced numerical differentiation equation solving in Wolfram in Mathematica. And well, in fact, I think it's a whole book. But one thing I found particularly useful, so say we want to solve a partial differential equation, like Einstein equations, you look at like this numerical method of lines, and it nicely explains like how are all these equations, and you can actually read it and see a little bit in Mathematica how this works. And there you'll find also things, that's how I got, for instance, this finite difference derivative. Right? So you just all explained in these tutorials, and that's how I got this. The alternative way is to get it out of a book, but I recommend really to use this kind of tutorials in Mathematica for NDSolve. Okay, so Mathematica constructs this matrix. You can test if it works correctly. What we also will need for our differential equation is the second derivative, or the second order equation. And of course, you can just apply the differentiation matrix twice, and you get the second derivative. Alternatively, you put a 2 over here, and then Mathematica constructs the second order differentiation matrix. And what we now want to do is, instead of writing the equation like this, we want to write it as a matrix equation. Because this equation is now basically, well, this is just, this yx will be our vector, because we want to do it numerically on the grid. And y prime of x will, of course, be the matrix which differentiates this thing times the vector. And this will be like 2 plus x times this second order matrix times the vector. And this is then basically what your differential equation looks like in terms of a matrix equation. And in the end, to solve this equation, we just need to invert that matrix and find this vector. So this should be 0 in the end, of course. And just by inverting the matrix, we can find the vector, and we basically solve the equation. So that's the idea. So let's look at the so this is the equation again. Let me also put it down there. So we want to convert this to a matrix, and how do I actually do this? Well, so if you look, we want to know. So say we want to represent this term in terms of a matrix. We need to kind of take this coefficient times this. So basically, what we want to write is to construct this matrix. We want to kind of make a matrix times our function y equals to some source or equal to 0. And this matrix contains these three terms. And the term of the y prime prime is basically, so the coefficient in front of the y prime prime, which I find by differentiating the differential equation with respect to y prime prime. So the d of L y y y will just be, of course, 2 plus x. So if you do this, indeed, you find 2 plus x. So x is our grid, so that is this one. 2 plus this, so minus 1 plus 2 is indeed this 1, and then it goes like this. And if you make a diagonal matrix like this, and you multiply this by this second order matrix, and you multiply this by this function y, then we are back at this term. So is that clear? Okay, so that is the first term, and the second term is even simpler, right? So we just differentiate the differential equation with respect to y prime. So we just get a 1 here, but Mathematica will do that, so that's okay. You put the differential equation, you multiply it with the normal differentiation matrix, and then in the end, we just need the diagonal matrix multiplying minus 20x times y, which is the last one. So note indeed that we're writing this as a matrix equation. This last one is just a diagonal matrix, because here every point is just multiplied by minus 20x, but these derivatives are actually dense matrices. So if we look at this D-spec, because it's all of the grid points are used, it's an infinite order scheme. So let's look at this matrix. It's an all order scheme. Then it's completely dense. Actually, you shouldn't make a sparse array then. I don't know. Did Mathematica do that? Yeah, Mathematica made it a sparse array, but it doesn't make sense because it's a dense array. You see some big numbers, and the idea of these big numbers is basically that this gives you using all the points gives you the most accurate approximation of this derivative you get. So this is the equation matrix, and then there's also a source term in principle. If we add a source here, then there is a source, which is just the differential equation of y equals 0, but in this case there's no source, so the source actually is 0. So that's true. So the equation matrix looks like this. Well, that's not very insightful, but we hope it's correct. So what we now want to do, we wrote this equation in terms of my equals s. So what is y? Well, it's just the linear solution of this linear system. So you do a linear solve, equation matrix minus source, and you try it, and it doesn't work. Why doesn't it work? Well, the reason is actually rather simple that it doesn't work is because this is a differential equation and we didn't put any boundary conditions. So this actually does not have a well-defined solution, and Mathematica actually finds this because this matrix is actually not invertible. And the reason why it's not invertible is also very simple, because if you take the derivative of some function f, the derivative of a constant function, this should of course give 0. So basically any constant factor, which is the same everywhere, gives you a 0, and this differentiation matrix knows this, so it has a 0 eigenvalue, and if you have a 0 eigenvalue, you cannot invert your matrix, and so this is why this actually goes wrong, and this is of course also true because we didn't put these boundary conditions, and as you know, if you have a non-invertible matrix, that means that few of these, well, in this case, actually there are 2 eigenvalues which are 0 because we have a second order system. So if the second derivative is 0, you have like either constant functions have a 0 eigenvalue, but linear functions also have a 0 eigenvalue. So if you construct this matrix, you'll find that there are two linearly dependent rows. So basically, we can chase any 2 rows. They're linearly dependent, so we can just change them. And we use these 2 rows, which didn't contain any information anyway, to put our boundary conditions. So in this case, we just use the first and the last one, because the first one is this grid point at -1. The last one is this grid point at 1. And our boundary conditions, what did it look like? It looked like this. And the boundary conditions. So we want to, in this matrix equation, we want to implement these two boundary conditions. So basically what I do is the equation matrix, the first row, and then, so I take the first element, so this is the first, no, it's the first row, and then all the elements just becomes this table. So it's 1. So this row is basically going to read that the first element in your vector equals something, which I should put in the source here of the vector we're going to do the linear solve. I guess I have to hurry up a little bit. And the last one is, of course, the other way around. So if we change this equation matrix, the first row and the second row, how does it look like right now? You can check it a little bit more easily. So now, indeed, we still have exactly the same matrix, but these two rows we didn't care about are now just the identity rows with the first element and the last element. And the source I also changed, so it was now not completely 0 anymore, but we had to put these boundary conditions. So in the first row it was equal to -5, and the last row it was equal to 1. And now we can try it again, and now we got a nice answer. So now, of course, because of these two rows changed, now I want to check if this is actually correct. So we had the previous plot, and we list plot this function we got, where we put all these points on the grid points. So if you fret x and this function, then you get the combination of grid points and these function values, and we can list plot that. And this is how the list plot looks, and this is how the analytic function looks. So indeed, we got a very accurate answer. Well, okay, so that's, of course, here you just see that, of course, you got all the points nicely on the right. So by eye, it looks good. But what I want to show you is actually compare with the analytic solution. So this DSOL LDE was the analytic solution. If you evaluate it for all the grid points, you get the analytical answers on all these grid points. And we have the function values also on the grid points. If we take the difference and we plot that, then indeed you see that these values are 10 to the minus 13. So with only 25 grid points, so here you see these functions go all the way to 10. You got more than 14-digit precision, and perhaps this precision is actually dominated by machine precision errors. So if you go to higher precision, you get maybe even more accurate results by using only 25 grid points. And just to compare, for instance, because we also solved here in the beginning this function, we're using ndsolve. So I can also compare how ndsolve did this. So you take the function value minus the ndsolve one, and there you see actually there's a big difference between the ndsolve one. So the spectral method with only one matrix inversion is actually, well, is 1 million times more accurate than the standard ndsolve one. And actually you might be a bit surprised because the ndsolve one actually got the boundary condition wrong here by 10 to the minus 6. Of course, I don't want to say ndsolve doesn't do a good job, because if you actually put the accuracy goal or the precision goal of ndsolve a little bit higher, it will probably get it correctly. And also, one thing I just implemented that yesterday. One of my favorite ndsolve methods is just to solve this equation using a explicit Runge-Kutta method, where you just have some step size, some difference order. Well, I don't want to explain all the details, but if you do it like that, then you see actually that the ndsolve also gives very accurate answers if you change this method a little bit. So you tell ndsolve what to explicitly use, then you also get a nice answer. But in my research, I usually use the spectral methods because it's very fast and very, well, you just need very few grid points. And if you use these kind of ndsolve methods, it can be a little bit slow. But on the other hand, it's also good to know that there are these kind of methods. And for your reference, if you download later on, I put here, did I put that over there? I thought I, yeah, well, I put these methods here so you can use these methods if you want to specify this, and you can also look this in the tutorial. Also for your, this I didn't want to present, but just for your reference, I took kind of the same spectral method by for time-dependent metric, and this very simple metric, it can solve by first looking at the Black-Brain solution, the perturbation, and just solving this spectrally. If you want to look at it later on this afternoon, we can go through it, how this actually works, and you get some kind of time evolution in ADS, some horizon here, some boundary here, you have some metric, it evolves, and if you extract it, you get these quasi-known modes. And this is just done using spectral methods and some ndsolve time-stepping solutions. So we can look at it this afternoon if you're interested in doing these kind of things. And here I put also two of my other ndsolve favorite methods. So if you have a time-dependent problem and your ND-solve doesn't give you the right solution instantly, I usually use this method of lines, and you can do some spatial discretization with some difference order. You can do it spectrally, or you can do some lower order scheme. You specify the number of points. Well, this Runge-Kutta I already showed, but just to give you some reference, you can look at it later if you're interested. And with this, I think I would like to stop. Yeah. Yes. So, in fact, this is a good point. Maybe Jason knows this, because I wanted to do, I tried this, I think, the day before yesterday, to solve this spectral method with these 25 grid points, just using exactly the same algorithm with Mathematica, and that I didn't manage, in fact. So I don't. So the different. At some point you can do that. I don't think here. Do you think it would work over here? Pseudo-spectral given for dimension should be a positive machine size integer, or pseudo-spectral. Good. Okay, so that gives the same answer. Yeah, that's a good point. But to really solve this, to tell ND-solve that it should use a differential equation and solve it pseudo-spectrally, I don't think you can do it, and you need to construct this matrix. Yes.
So the pseudo-spectral argument you need to use initiation is very respect that's the basis.
So in this case, in fact, in some sense, I just use spectral methods by specifying where these grid points are. So if you specify where these grid points are, then it constructs, these all-order polynomials. That's what this finite difference derivative does. And that effectively uses these Chebyshev polynomials. But in this kind of implementation, it's completely gone, except at the points where you put the grid points. You're basically using the fact that we have to put the grid points over here, and we have to expand in polynomials. And that's what Mathematica then gives you this differentiation matrix, and then everything follows in the similar way. Yes. Yeah, so you don't even have to know about these Chebyshev polynomials. That's actually true. That's also true. Okay, last question there. Yeah, I think at some point I looked a little bit into this, and so the point of the spectral methods, if this works, like 25 by 25, just doing a linear solve is super fast. That requires like 1,000 operations, so it's there instantly. And ND-solve, of course, has very advanced algorithms. Probably I should also mention that these pseudo-spectral methods don't always work. So this kind of, because you're doing this super accurate expansion in terms of these polynomials and having all these derivatives almost analytically, if you don't have an analytic function, so for instance, if there could be something here like x log x. The derivative of x log x goes like log x. So at 0, the function would be continuous, but the derivative would diverge. If you try to expand the derivative which diverges in terms of these polynomials, you'll have very bad results. So this pseudo-spectral works for some problems, like these Einstein equations works very well, and then it's very fast. And otherwise, you have to probably go to other methods. Yeah, okay, so I still have 10 minutes. That's actually a good point. So I could say a little bit how to do these coordinate transformations, which I did in this, which I wanted to explain with this metric. Well, I can just put down the metric. I mean, it's one metric. You can do other metrics. The Einstein equations is just the Ricci tensor plus 4 times the metric. What I wanted you to show is one thing I often use, and which is really not needed in this kind of problem, is that I wanted to make these functions. So we have some Einstein equations, and the first one looks a little bit oh, the first one is 0. But the second one is non-trivial, and it looks like this. But this function b, we want to do a linear approximation. Say we want to do that. So we want to have this b going to some function like b0 plus a small perturbation epsilon times delta b. Just to put it like this. But I want to do this for all my functions I have in the metric. And in this case, there are only 3, so I just could copy paste. So it doesn't really, it's not really needed to do this to automate this. But here I did it anyway to show you how I use this actually when you have a lot of functions. And what I want to do is this function b to b0 plus epsilon times delta b. And this is not super easy because I want to really add, if I call my function b, I want to really add this b0, this 0 to the b. So what I do is I do a toString of this b, and then I add this 0 as a string. So here you have this function f, and if you put here a b, then you can add this 0, but now you get back a string b0. So that's also not what we want, because we do want an expression. So what you then do is you do toExpression b, and then you have your expression b0 back. And the same way you can do by adding this delta, and then there's this epsilon, and then you want to redo these replacements of functions as a function. So basically what I then have is this rule where you have this toExpression b0 plus epsilon times the delta b0 for all these functions I have, and in this case there were only 3 functions. But then you construct this rule where a goes to this expression. And what we see, for instance, if you have a time derivative of a, so it looks like this, and we apply this rule, which I call to a linearized regime, because we want to go to a linearized regime, then you just apply the linear rule, and then indeed the derivative of a as a function goes to time derivative plus epsilon times another time derivative. So that is this replacement of functions, which I use very frequently. Also, what yeah, so for all these functions, a goes to the toString plus the 0, and the delta to the a. And you do it as a pure function. That this looks nicer? Yeah. What is? Good. Okay, so and then I got my linear Einstein equations, and one thing I kind of deliberately put here in the metric, I put some r coordinates. So this ADS boundary is at r equals infinity in this case, but actually usually this is very impractical. You want to go to 1 over r coordinates where the boundary is at, so u is 1 over r, and then the boundary is at u equals 0, because then you have your grid nicely from 1 to 0. So you want to do coordinate transformations, u goes to 1 over r, for this whole equation. So how do we do that? That is also very easy in Mathematica. So you make this function replace r to u. And the tricky thing is that there are all kinds of derivatives to r. So basically what we want to do is we have the Einstein equation again. So the second one, well, now we have the linear Einstein equation, so it's a bit more complicated. No, that one is actually, yeah, the linearized Einstein equations are simpler, of course. So I think the fourth one still has all these r's and r derivatives only of this delta b left. So now we want to do this coordinate transformation where r goes to 1 over r. And I want to make a rule where all of these, so basically for any function f, for any time derivative and any r derivative, I want to know what does it look like when I did the r goes to, so the u equals 1 over r type of transformation. And the trick here is, which I had to think a little bit about, but which works very nicely, is that you let this, so the time derivative doesn't change. So you still have this function f, and you want so you take the time derivative of f 8 times. How do I, well, usually you actually, how do you make this? I usually make this notation just by doing like ft 1 over r, take the time derivative, and then you copy paste this f 1 over r, you paste it over here, and then you don't want to have it once, but you want to have it 8 times. So now you can just use this Mathematica notation with the time derivative like this. If you don't copy paste, but you just do the brackets up there, then Mathematica wouldn't recognize it. But this is how you generate this notation. And the trick is, of course, that the r derivative after this transformation is just the u derivative basically, but then u is 1 over r. So the trick here is that so you differentiate. If in the new coordinates I differentiate with respect to r here, 1 over r, then I should get more or less the right answer. So if I apply this rule to delta b, so the first derivatives as an example, and I apply this rule, what do I get is, and you can check, of course, that this actually, if you do the normal coordinate transformation yourself, that this is the right answer, that this, you get the derivative, but if you differentiate this delta b t 1 over r with respect to r, Mathematica automatically does the chain rule as you want it to do it, and you get this 1 over r squared. But you now have to remember that with 1 over r, I actually mean u. So that is what I do after this coordinate transformation. Then I change again, r goes to 1 over u. And u still has some values, so I should delete that. And this is then indeed the coordinate transformation. And the nice thing about this rule, of course, is that if you have the fifth derivative, then it would require some work to do it by hand, but you can still do it, and it works still the same way. So this is a useful thing I use very frequently. Sorry?
You could also do it with slightly faster. You can do f underscore t and r goes to so remove the derivative stuff.
Oh, is that true?
And you can say it goes to, well, let's first say, you can say x still. Notice. I changed my mind, sorry.
Well, you want to say that you want to do it as a pure function,
Yeah,
so f.
but then of course you cannot do it as, sorry.
Maybe this actually works. Like, you say it should work like this?
No, this kind of thing will work, but you cannot do it to x. You must put delta b.
Why doesn't it recognize? Oh, that's true. That is true. That is true. And this gives then, okay, but at least it's a good check that this gives the same answer then as my formula. Does it give the same answer? R goes to 1 over u then? Well, now it gives it the other way around, right? It does give the same answer, right? Yeah. Good. So yeah, okay, so I guess this is indeed the reason why I probably tried it like this, and because you then it doesn't recognize this pattern then, right? That is probably the problem.
Yeah, you have to look for this, your way.
It was a bit of a trick, and that's actually why I wanted to show it, because otherwise, well, this is what I use very frequently. And well, I mean, for instance, then how you then modify this equation a little bit more. I guess I now have 1 minute left, but so this delta b turns out that delta b at the boundary goes like u to the power 4 if you do the near boundary analysis. You have to look a little bit at that. Okay, I shouldn't do this in Mathematica notation, but if you then want to solve it numerically, it's usually very convenient to redefine delta b as being equal, by definition then, as delta b regular times u to the 4th. Because then, if delta b goes to u to the 4th, then delta b regular is just finite at the boundary, so just a constant value. And in fact, it's related to the stress times anisotropy in the field theory. So this is then what I usually do is delta b just goes to this delta b regular times this thing to the 4th power, which of course you need to figure out independently by doing this near boundary analysis, which you can also do in Mathematica. I really replace the r to u, and then you really get this nice equation where this delta b is perfectly nice and finite, and there are also no divergences if you choose u equal 0 to 1. And this then, well, in fact, this equation you can solve using ND-solve very easily, but below here I did it in the same way with the spectral methods, where in this case, actually, so this is a second order, two-variable equation, of course. So how you solve this equation is actually a little bit trickier, because now what we're doing, we're starting with some delta b regular at a fixed time slice, and then we want to use the spectral methods to compute the time derivative of delta b regular, because you see that here there's a time derivative and a u derivative, and here there's a time derivative. Well, these are just u derivatives. So these you can, if you know delta b at a fixed time, you can evaluate this one, and this one, because you know that's a function of u. But you don't know the time derivative, and you see that this is then, in a similar way, a first-order linear differential equation for the time derivative of delta b, which you can then solve spectrally. So then you get the time derivative. And then you step forward in time, and then you repeat the whole procedure. And the stepping forward in time, I usually also implement myself using this type of Mathematica code. But in this simple example, here I did the spectral method, just like we did before. I did the time derivative. I defined what the time derivative is using the spectral method with the linear solve. But then the time stepping I just did using the ND solve. So here I just say that the time derivative is my own time derivative, and then just solve it from t equals 0 to 8. And then Mathematica is actually quite good in doing this time stepping because it has this, it changes the time step as it goes through the solution. So if I would do it myself, I would always just do like a 0.001, 0.001 with a fixed time slice. But this has an adaptive time stepping, so actually it's not so bad using this ND solve as opposed to writing your own algorithm. But of course, you can also specify what kind of time stepping ND solve should use, and then you know exactly what you're doing. And you get solutions like this. Okay, let me stop that like that.